In this video, I will talk about current densities and the different kinds of current densities that we have. I'm going to start with the linear case, the one-dimensional case. I did start with the definition of the current, and now I'm talking about conventional current. A small current, delta I, is equal to the small amount of charge that passes by through a cross section of my conductor, of my wire, over the change in time that it takes for that charge to pass. And I start with the linear case. Let's say I am here and I'm here and I'm looking at how much charge is passing by from this point. Okay, then I can write in the, let's say, from here to there, it takes amount of time delta t for the charge from here to here to pass from this point. So I'm gonna write the charge delta q as lambda, the linear charge density, times delta L. Okay, lambda times delta L will give me the total charge included from here to here, and this is how much charge passes by from this cross section of the conductor in time delta t. And then I have delta L over delta t. By definition, when you have the distance over the time, you get the velocity. So the linear charge density lambda times v, this will give you the current in the linear case. Now, something similar we do when we deal with surfaces. Okay, I start with the same thing. Now I have a surface. I have the charges. Let's say the charges are flowing this way. Now, if I am here and I'm looking at how much charge is passing through this portion of the conductor, then I will write the charge delta Q as sigma, the surface charge density, times delta A. Okay, when you deal with surfaces, delta Q is sigma times the area. And then I'm gonna do the following for the area. Let's say that whatever charge is included in this area, this is the charge that passes from this cross section of the conductor in time delta t. So the area delta A becomes delta L perpendicular, which is this, and delta L, which is that, right? It's a rectangle, so that's how I can find the area. And then what I do, I say delta L over delta t again. This is V, so this becomes sigma times delta L perpendicular times V. Now we define the surface current density to be the small delta I over delta L perpendicular. And if you take the left side and divide it with delta L perpendicular, we will get sigma, the surface charge density, times the velocity. Okay, so this K, this is the surface current density. This is the surface charge density. So this is in 2 dimensions. And then when we move on and we have volume charge densities, moving in the 3-dimensional wire, I start again with the same definition. The charge delta Q is the volume charge density times the small volume delta V over delta T, and then I can write a volume. Okay, a volume of delta V can be written as the area times the length delta L. Now I can write, as usual, I will write this as the volume charge density times the perpendicular area times v, and this is the velocity. And similarly with the 2 dimensions, we define in 3 dimensions the volume current density J, which will be delta I over delta A perpendicular. This will be the volume charge density times the velocity v. Now, to summarize, okay, for volume, for 3 dimensions, I have the volume current density, the volume charge density times velocity, and when we deal with 2 dimensions, the surface current density is the surface charge density times velocity.